Last but not least, for this purpose of taking some volume integrals, we take our chance and derive the well-known expression for the volume of a sphere, which you all know from school, but almost nobody knows where it comes from, actually. At least I myself, when I was in school, nobody explained to me where this interesting formula comes from. Well, afterwards, it's clear why they didn't tell me, because I wasn't able to solve a volume integral back then, and you weren't either. Well, anyway, we take the chance and set up a volume integral, which gets us the volume of a sphere. And in order to do so, we have to integrate along the inside of a sphere by summing up volume elements differentially, or in other words, continuously. And this means that we have to put this in the form of an iterated integral, of course, using spherical coordinates. And here I take the result from the previous part, just using the geographical, you could say, version of spherical coordinates, which are not really 100% geographical, of course, yeah. It's just an analogy. And you remember, it's important that the theta angle has to increase from negative pi half to positive pi half in order to use the Jacobian factor of r squared times cosine of theta, not sine of theta. So that's fixed, okay? We found out clearly why this is so. Also, since I'm just summing up volume elements, all I have to do is express this differential volume correctly using the Jacobian, which is r squared times cosine of theta, times then taking the product of all the spherical coordinates, d phi, d theta, dr. The order is relatively arbitrary because the limits of integration are independent of each other. You know why? It means, you could say, this is a three-dimensional, you could say the integration area is really a higher dimensional sort of a type 0 region. It's a type of region where you do not have any dependence of limits of any variables at all. You just have fixed values. And that, so you could say, in an abstract sense, that the sphere is sort of a cuboid if expressed in spherical coordinates, right? If you imagine this were x, y, z, this would define the inside of a cuboid, as in part one of this exercise. But of course, it's a sphere, and that's why we've done this whole effort of taking the Jacobian matrix and so on. Yeah. Now let's just start. What we see here is that this term depends on r and theta only, not on v, not on phi. Sorry, and because this is the case, we may easily perform the phi integration by just multiplying the factor which corresponds to the length of this phi interval. So this is the contribution for going once around the z-axis, right? I could also say, leave this term alone, take the primitive function with respect to phi, which is then this term times phi, and then insert from 0 to 2 pi. But in the end, it's a factor of 2 pi, which I may draw outside. Yeah. So the phi integration is done, and what stays is an integral over the remaining r squared times cosine of theta, first over theta, then over r. And you see what I'm doing here. It's not necessary, but perhaps it's better to do it. I may move this factor of r squared just a step to the left, namely outside of this theta integral. Why? Because it's not affected by this integration. So I can just leave it alone and put it there where it belongs, where it has to be considered later, right? And so the integral I have to solve now is an integral of cosine of theta over theta, and then inserting from negative pi half to pi half. That's what I'm doing. And I get as a primitive function, I get the sine of theta, and then I insert from negative pi half to pi half, which is always the same. And here, Evgenia, you remember, and this was the problem. If you take limits from 0 to 2 pi, now you get 0. After all, sad result. No matter how big a sphere, its volume will be 0. Of course, we agree this can't be the case. So this is correct, and we get the sign of pi half equals 1, and the sign of negative pi half equals -1. So the contribution here is 1 minus -1, which is actually a factor of 2. And that's all. And what remains is, drawing this outside, 2 pi times 2 gets us 4 pi. Interestingly, this is already, and it's actually exactly the result for the surface of a unit sphere, and for not by chance. This is what we've calculated by now, because the R integration is what comes last, and the R integration tells us to integrate R squared still over R. Here it is, and of course the primitive function here equals R cubed over 3, and that's it. And there we have to insert the radius variable ranging from 0 to capital R, the radius of our sphere, which is fixed. And then so we insert capital R for the regular R first. So we get capital R cubed over 3, and then minus nothing, 0 for R. And so that's it. We get an additional factor of capital R cubed over 3, and drawing everything together, this is the result: 4 over 3, 4/3, times pi times radius of the sphere to the power of 3. That's the famous result for the volume of a sphere. And quite interestingly, I'm sorry, my daughter, Janisa, when she was in, I don't know, in the 10th class or even before, she found out that the derivative of this formula, if you take the derivative, just considering R to be a variable, just for your interest, derivative of this gets 3 times, everything, and then R squared, and the 3 cancels out, and what remains is 4 pi times R squared. And she told me, Dad, it's interesting that if I take the derivative of the volume formula for a sphere, I get the correct formula for the surface area of a sphere. And I told her, this is just fantastic, because what you've just found out is a true fact, which has a definite explanation if you consider what you're doing when building up a sphere, the inside of a sphere, by adding volumes of little spherical, how do you say? I don't recall the term. Spherical surfaces with a thickness. Yeah, you just sum them up to get the total volume of a sphere. And the reason is, if you take an integral of this one over the R, okay, by this method, what you get is the volume of a sphere. And that's so interesting to see that by a polynomial differentiation rule, which you've learned, which you learned in the 10th class. You find that there's a simple connection between these formulae. This is also a trick to remember them. By the way, the same holds for taking the famous formula for the area of a circle, with the, I keep using this notation, PR squared. If you take the derivative, you get 2 times P times R, which is the circumference of the sphere. And this is for the same reason, building up a circle by adding, little circumferences with thickness. By adding them up, you get the area of a circle. I like this. I hope you like it too. But that's it. That's the end of this exercise. Thank you.